Hello and welcome to this webinar on system identification. My name is Lennart Ljung and I am a professor of automatic control at Linköping University in Sweden. I am the person behind MATLAB's System Identification Toolbox, and I will introduce you both to that toolbox and to the basic art of system identification in this webinar. System identification is the art and science of constructing mathematical models from observed data from a dynamic system. A dynamic system is a system with memory. How it reacts to your inputs depends on what you have done previously. Mathematical models are playing increasingly important roles in today's science and engineering, and they are required for solving a number of tasks, like simulation, control design, and proper signal processing. It is important to master various techniques for model building. There are two ways of modeling dynamic systems. If you know the physics or math behind a problem, you should make use of that knowledge to form the model. This is known as first principle model. If you don't know the physics in detail, but you have measured data from the system, use that data to construct a model. That we call data-driven modeling. MathWorks offers several products for modeling systems: Simulink, Simscape, SimMechanics, Blocksets, and other first principles tools. Simulink Design Optimization, System Identification Toolbox, and the Neural Network Toolbox are data-driven tools. If you make use of both physical insights and measured data, we talk about grey box modeling. The System Identification Toolbox and the Design Optimization offer several tools for grey box techniques. Together, these products provide a complete solution for modeling dynamic systems. So to pinpoint the notions, a system is a real thing, like an aircraft with input signals, rudder and aileron angles, thrust and so on, and outputs being velocity, aircraft, attitude, like pitch angles, etc. A model is an object where you replace the real system with mathematical expressions. These expressions create a similar relationship between the input signals and the output signal. We should generally denote the inputs by U and the output by Y. The essence of system identification techniques is then to subject both the actual system and the model to the same inputs and compare the real response with the model's output. The model parameters are then adjusted so as to minimize the size of this error. So the key feature is to provide a model that produces an output that is as close as possible to the measured system output. We can inspect the success of a given model by plotting and comparing to these two curves. We see here as the gray curve the true measured output, while the blue curve is the model's response. A numerical measure of fit can compute it as a percentage of a measured output variation that is reproduced by the model. This particular plot shows a fit of about 60%. Let us test these ideas on some real data. Here we are in MATLAB's usual command window. I load a data record. It contains measured input and output signals from a system. You can analyze and work with a data record entirely in the command window. It is typically easier to invoke the graphical user interface, the GUI, and work within that. I open the GUI by typing ident in the command window. The GUI basically consists of a number of frames for datasets to the left and the number of frames for models to the right. The steps of system identification are basically carried out via two pop-up menus, one for pre-processing and polishing data, and one for estimating models. By these pop-up menus, you can reach all the essential functions and commands of a toolbox. Let us give a first demonstration of how it works. The data signals I loaded into the workspace can be imported into the GUI by selecting Import Time Domain Data. I write U for the input, Y for the output. I say the starting time is 0, the sampling time of the data is 80 milliseconds, and I gave the dataset the name dryer, and I import the data. You can see that the data set is now inserted into one of the data frames. We can examine the data by plotting it as time domain signals. The data are collected from a hairdryer. The input is the power applied to a heating device at the inflow of the air, and the output is the temperature of the air at the outflow. We can also look at the frequency contents of the data if we check the data view data spectra. We can estimate different models using the estimate pop-up. We shall later on talk in much more detail about the available choices, but let us now first pick a standard type of model, a linear transfer function model. You see here that we can decide the number of poles and the number of zeros of the model, and whether it is in continuous time or in discrete time. Let me pick a very simple model with one pole and no zeros in continuous time. I give a name, the default name TF1 to the model, and I estimate it. And we now see that the model has been inserted into the model board. If I double click on the model, I can see the value, the transfer function of it, a very simple first order transfer function. For the moment, we are not interested in the mathematical details of the model, but I would just like to see how well it can reproduce the data. I mean, look at the data fit. I do that by checking the model view, model output. It creates the comparison plot I discussed before. The black curve is the true measured output, and the blue curve is the model's response to the same input. This first order model is not very good at reproducing the measured output. It just gives 47% fit. So let us try some more flexible second order models with 2 poles and 1 zero. That's called TF2. So I estimate that. We see that the new green model is much better. The fit has jumped to 86%. Can we do even better? Let us try higher order models. I first try a model with 3 poles and 2 zeros. And let's try one with 6 poles and 5 zeros. So these models, the red and cyan model has now been inserted. They show even better fit. The third order model has a fit of 92%, and the sixth order model has a fit of 95%. So how far can we go in the model fit? Well, we can try a very flexible non-linear model of neural network type. There's a special webinar on non-linear models, and I will not give any details of that, but just think of this as a very flexible model with many parameters. I pick 10 delayed inputs and 10 delayed outputs, and I pick a non-linear structure being a sigmoidal neural network, and I estimate the model. That is now inserted into the model board as the NL-ARCS1 model. And look at the fit. Amazing. It is a 100% fit, a perfect model. But is there a catch? When you think about it, it is clear that you can get arbitrarily good fit to the data by just testing flexible models with more and more parameters. The catch is that you should not be impressed by a good fit to the data that you use to fit a model. We call that the estimation data. The real test is when you evaluate the model on a new segment of data. We call that validation data. So while the fit becomes better and better to estimation data, when the model becomes more flexible, it will reach a minimum and then become worse when you test models on validation data. You will then no longer benefit from adjustment to the particular artifacts of estimation data. That is known as overfit in this context. Let us test it in our example. We have recorded another dataset, V-dryer, from the hairdryer. I have loaded that into the workspace and I now import it into the GUI. V-dryer. Import. It is now inserted into one of the data frames, and by checking the data icons, I can decide upon which data to look at. The V-dryer record is for the same system, but for a different recording. The input changes a bit faster, but otherwise it's quite similar. Let us see how our five models can reproduce the validation data. You should note that the model output view is computed for the data record that sits in the validation data frame. So if I change the earlier set dryer that I use for estimation to the new data set V-dryer, all the fits are recalculated automatically. So what happened? Now the previously perfect model NLARX1 has gone wild. It is unstable and kind of disappears into infinity. To see if it fits better, we have to remove this model by clicking on its icon. We see that the third order model TF3, the red curve, is now the best model and reproduces 80% of the output variation for this data set that it has not seen before. The more complex sixth order model TF4, which was a touch better on estimation data, is now a touch worse. Our conclusion must be that the model TF3 is a good and robust model of the hairdryer that can reproduce the system behavior under various conditions. We will now spend some time on discussing the general nature of system identification. The workflow follows the following scheme. First, collect experimental data. It is good to get at least two data sets, one for estimation and one for validation. Then estimate models from data. That involves two steps. First, decide what model structure to use. Then estimate the best model in that structure. The graphical user interface, the GUI, may provide a good guide through this workflow. Finally, validate the model by confronting it with independent data sets. In that way, we are assured that we have not overfitted the data to the artifacts of a particular data set. I may add that in this process we do not only get a model of a system, but also some indications about how reliable it is. We get measures of the uncertainty of a model as well as how much of the output is affected by its disturbances. This may be quite useful, for example, for robust control design. Let us comment in somewhat more detail of the different steps in the identification process. The input-output data that we collect may be sampled time domain signals. It may also be measurements of their Fourier transforms, that is frequency domain data. Or it could be measurements of the frequency functions of a system, obtained, for example, by a frequency analyzer. I have denoted here in red names or toolbox commands that are relevant for the applications. Designing experiments that produce input and output measurements that carry suitable information about the system requires some thought and also insight about the character of the system. It involves questions like what sampling rates we should use, what frequency contents is suitable for input, etc. When the data has been collected, it is necessary to have a critical look at it and also possibly polish it. It can mean things by removing offsets and trends, looking for missing data and outliers, pre-filtering to remove bad disturbances, and more. The next problem is to select a suitable structure where to look for a good model. This is no doubt the most difficult step in the identification process. This is because there are so many possibilities and because the success of a model may critically depend on the choice. Later on in the webinar, we will look at a few specific examples, but for now, let us just recognize that the toolbox offers a wide variety of choices. So how do we know which model structures to test? It may be that we have prior physical knowledge. For example, that the system is known to be nonlinear. It may be that the intended model application requests a model of a particular kind. But in the typical case, we do not know really what to test. The basic advice is then to stick to a number of standard structures that can prove useful. One should be generous at this step and try many choices. After all, it is likely that you have spent quite some time and money on collecting the data, so spending a few seconds more to compute the model in a new structure seems like a quite reasonable effort. The next step to find the best model in a given structure is really the main duty of a toolbox. It may involve a considerable amount of computations, but it is conceptually straightforward. The final step is the acceptance test of a model. We should have found a candidate model that is the best we can achieve by trying various model structures. But is it good enough? Will it solve the task we have in mind? The final test is, of course, to try it out on the application. But before we do that, we should try to get some confidence in the model by twisting and turning it, looking at different aspects, confronting it with various data sets from a system that it should be able to handle. There is no clear-cut procedure for this, but I will comment on a few specific methods later on. It is important to realize that the system identification is not a straightforward one-shot procedure, but is rather an iterative procedure. It involves several decisions, which may have to be revised in the course of an iterative approach. We may have to go back and try a variety of model structures, or even go back and collect a new data set if it turns out that the first one was not informative enough. Let us now turn to what I call the most difficult problem to find a suitable model structure. There are a few general features to this problem. First, do we have any prior information about the system that will guide the choice of model? If not, we have to stick to flexible model structures with considerable approximation power. We call that black box models. Or if we know, for example, as in the aircraft case, a fair amount of the physics describing the system dynamics, Newton's laws of motion, etc., but are uncertain about the number of constants, like the aerodynamic derivatives. We should build a model that incorporates that physical knowledge that we have with the unknown physical constants as parameters. That is known as gray box models. Another key question we could ask is whether we are looking for a linear or a non-linear model. A third basic question is whether we are content with a model that describes how the input affects the output, or if we also want a description of how the output is affected by load disturbances. This webinar basically only deals with linear black box models. It is now time to get back to the graphical user interface and recognize the basic steps of the identification process. Designing an input signal and collecting the data lies outside what you do in the GUI. But once the data set is inserted, the pre-process pop-up allows you to process the signals that reside in the working data slot. For multivariate data, you can select subchannels. For multi-experiment data, you can select particular experiments. You can select certain ranges of a signal, detrend signals, and you can also filter the signals through various bandpass filters. You can transform the data between time and frequency domain representations. For example, here I transform our Dwyer set to its Fourier transforms, creating the set Dwyer FF. I can transfer any data set to the working data slot and to the validation data slot at will. With the estimate pop-up, I can estimate models from the data set in the working data slot. The pop-up supports a variety of model structures, and I shall shortly talk about a few of them. The created models can be examined by different views. You have seen the model output view before, and that simulates the model using the validation data. Normally, I keep the validation data frame populated by an independent data set, so as to quickly see if a new model is a better choice. The created models can be rearranged at will by clicking and dragging. I can throw away models I don't need by dragging them to a trash can. And I can export them to the workspace and to have a further look at them. So let me export the good model TF3 to the workspace. And now it's available in the workspace, as you see here, TF3, if I write in the workspace. Here we see the model. So here I can now continue, if I'm interested in control applications, for example, by applying all kinds of control system toolbox tool to this model, like CISO tool, etc. As I said, the estimate pop-up gives a concise summary of what model structures are available. I encourage you to explore the possibilities on your own. Let me comment on some of these structures in a little more detail. So here we have the three main cases of model structures supported by the GUI. The most common class is no doubt linear parametric models, and I will turn to these in a minute. Later on, I will treat linear non-parametric models. Non-linear models is a rich and interesting topic. However, they fall outside the current webinar. Linear parametric models can be written as input-output transfer functions, where the input relates directly to the output in a difference or differential equation. These equations are often written in terms of Laplace or Z transforms. They can also be written in state space form, using a state vector as an intermediate variable. The flexibility or size of a structure is described by one or a few integers, the number of states n, or the number of terms in the numerator and denominator of a transfer function, that is the number of zeros and poles, nz and np. Actually, the transfer functions and state space models are two sides of the same coin. They both describe the model with linear difference and differential equations, and thus cover the same set of relationships between input and output. The difference is how they are parameterized in terms of polynomials or matrices. There is one more feature that is essential for models. Often there is a delay or dead time in the system. That is, a time interval passes before the input affects the output. In our hairdryer system, for example, it will take some time before the power change in the heating part affects the outlet temperature, simply because it takes some time before the air has been transported to the outlet. It is important to get an idea of this delay time. It could be estimated or measured from data, and it will be part of a model. For a discrete time model, the delay is an integer, the number of sampling intervals before the input reaches the output. That means that linear parametric models are characterized by a few integers, the orders and the delay. To estimate such black box linear models, we just need to select these integers. Another common type of linear parametric models is to form a simple model with one pole and one time delay. It can be parameterized in terms of a time constant, the static gain and the dead time. Such models are quite popular in process industry, and we call them process models. More complex variants can contain more poles and an integer or a zero. To estimate such models, we just need to specify the number of poles and whether or not you should include a time delay or a zero or an integrator. I said that the nature of the airflow in the hairdryer indicates that there should be some time delay in the system. Suppose that we let the input be a step at time 0. We should then see how long time it takes before a reaction is visible in the output. Even if we have not collected such data, we can subject the models to such an experiment. That is done by checking the box Transient Response in the model views. And let us look at the step response of TF3. We see that it takes about 0.2 seconds before a response of the input step is visible. This means that we could perhaps build lower order models with this time delay. Let's try that with the transfer function models. You see that the transfer function dialog has a segment about input-output delays. Here we can specify the delay to a fixed time or ask that it be estimated from data by unclicking that the delay is fixed to a given number. Let us try a second-order model 2 poles, 1, 0, and the delay of 0.2. And I call that model TF202. I could also estimate the number of the delay in this model by clicking fixed. So we're looking for a delay between 0 and 2.4 with the same number of poles and zeros. I call that model TFDE, like a delay estimation, and I estimate it. We see that the step responses of these two new models, TF202 and TFDE, are practically the same as TF3. And we can also look at the model output and see that they are practically the same fit, all of them, to validation data. We should then keep in mind that TF202 and TFDE are lower order models than TF3, so they are simpler but have a time delay. To estimate a process model, I pull down the estimate menu to process models, and the dialog opens where I should make some simple choices. Let us first try a simple model with one pole and a delay. It's called P1D, and I estimate it now. And we'll see here the step response is pretty much the same, but the model output has a worse fit, 57% compared to almost 80%. But we see that the delay is estimated to 0.247, which is kind of a correct delay estimate as from the previous experiments. We could try also a model with 2 poles, call the result P2D, and estimate the model. And we have a now a slightly better fit, 62%. So it's almost the same quality as we have seen before with these simple process models. An important issue in modeling concerns how to describe noise and disturbances. All systems are affected by other stimuli in addition to a measured input. We call that noise or disturbances. Essentially, it is like an other but unmeasurable input, including a model for how the disturbances affect the system gives 2 important advantages. If there are some systematic correlations with disturbances, that might help forecasting future outputs from the system based on observations of past outputs. The disturbance can formally be treated as an additional unmeasured input, simply by adding it to a transfer function or state space model in the same way as U enters. Since E is not measured, we must assume that it has some predetermined properties, typically that the disturbance source E is white noise, that is, E is a sequence of independent random variables. Measured outputs contain disturbances, so observations of past outputs give information about disturbances. If they are correlated over time, we can actually guess future values of disturbances. So with a disturbance model, we should be able to predict the future outputs better. Let us check if we can obtain better predictions for our hairdryer data using a disturbance model. Let us first discuss state space descriptions with and without disturbance models. Let us estimate a state space model of order 3. I pull out the state space dialog. I pick order 3. We see the basic system here with an input U and a noise source E. I now first estimate no disturbance model, so I fix K to be 0. And I call the model M3. And I estimate it. And I look at the model output. It is pretty much identical to TF3 in performance and step response as we saw previously. This confirms what I said, that the state space model and the transfer function models are two sides of the same coin. Let us now also estimate the K-matrix. So we build a model for how the white noise affects the system. And I change the focus to prediction. We call that model M3dist for disturbance model and estimate it. We can compare this model M3dist with M3 in terms of simulation performance. We see that M3dist is slightly better actually. This is because the noise model allows better weighting of information in data. But let us now check how the two models are capable of predicting the output 5 samples ahead. That is, we let the models have access to all inputs and all outputs up to a certain time, and we ask it to guess the output 5 samples later. I do that by selecting under Options, 5-step ahead prediction. And the responses are recalculated. For M3, without disturbance model, the predicted output is the same as the simulated output. But the disturbance model in M3dist now knows how to use the information in the previous outputs to forecast future disturbances, and that is clearly beneficial. The fit is improved by about 2.5% units to 82.4%. One would guess that the effect is more pronounced the shorter the prediction horizon is. I can select the horizon under the Options menu, and I now select 1-step ahead prediction horizon 1 step ahead. We see that the model that includes disturbance descriptions gives a very substantial advantage predicting the output 1 step ahead, 89% fit compared to 80%. I can also look at the error between the predicted signal and the measured output by selecting the error plot option. So we see here the 1-step ahead prediction errors. If we look at the M3dist only. So we see here the 1-step ahead prediction errors for the model M3dist. In fact, when you estimate a model that includes a disturbance model, it is this 1-step ahead prediction error that is minimized with respect to all the model parameters. That explains the term PM, prediction error method, for the estimation technique. The 1-step ahead prediction errors are that part of the output that could not be reproduced or explained by the model. They are, so to speak, the leftovers or residuals of a model. They contain a fair amount of information about the success of a modeling. So what the model leaves unaccounted for are the residuals, the 1-step ahead prediction errors. They should be uncorrelated with what you knew at the time of a prediction, like past input signals. Otherwise, we should have been able to do a better prediction. So how do we know if the residuals are acceptable? We should estimate the correlation functions and see if they show significant correlation. Here we see the cross-correlation function between residuals and inputs. It should ideally be 0, but may of course show some random variations. The significance of the estimate is here illustrated by a yellow band. Anything outside this band is an indication of significant correlation. Here we see the autocorrelation among the residuals. If we have built a successful disturbance model, the residuals should be white, so that this function should lie within the yellow band. So let us try that on our data set. By checking the model resids box, we obtain a plot of a sample cross-correlation function between the residuals and the input. For model M3dist, this correlation plot is the lower plot here. If the dashed lines mark the confidence region, if the curve stays within these limits, there is no significant correlation between the input and the residuals, and the model has done a good job. The upper plot is the autocorrelation among the residuals. If we have built a disturbance model, the residuals should ideally be white, that is uncorrelated with each other. We see here that the model M3DIST with a disturbance model has done a good job. But without, if you take a look at M3, we have very clearly correlated residuals among themselves. Analyzing residuals in this manner is a very good tool to get an indication if a model is good. Let us build a too simple model, a first-order state space model. Here, I call that first order. I call the model M1, and I estimate it. And in the autocorrelation plot and cross-correlation plot, we see clear indications of correlations between the residuals and the input. So there's more to squeeze out, or more information to squeeze out from the data. So far we have discussed parametric estimation methods, that is, methods where parameters in certain models have been estimated. Let us now turn to methods that directly estimate curves that are relevant and sufficient to describe linear systems. They are methods to estimate transient and frequency responses. They can typically be directly estimated from data, and generally I recommend to initially take a quick look at these curves to get a feel for the system properties right away. The transient response of a system is the output where the input is a short pulse or step. Of course, this transient response can be recorded directly from an experiment where the system is subjected to a step or a pulse in the input. In fact, simple step response experiments may be the most common example of identification experiments in practice. It is in any case a very valuable first stage in understanding system dynamics, typical timescales, delay times, and similar. For a given model, we can of course always determine its transient response by simulating the system with a step or impulse input. There are also techniques to estimate directly the transient response from any experimental data without assuming any particular model. Essentially, that is achieved by estimating a flexible high-order linear model. The frequency response is the system's response to sinusoidal inputs. If we apply a sinus function with a certain frequency omega as input to a linear system, the output will also be a sinusoid of that same frequency, but with different amplitude and phase shift. This amplitude change and phase shift is a function of frequency, is the system's frequency response, and plotting these two quantities as a function of frequency give the Bode plot for the system. This can be done by direct experimentation by subjecting the system to input sinus functions of different frequencies. This is called frequency analysis. For any given model, the frequency function can be directly derived by just inserting certain complex values in the transfer function of a system. There are many techniques to directly estimate the frequency function from any experimental data set. Such techniques are known as spectral analysis and are closely related to the use of Fourier transforms. Let us now try the non-parametric techniques for the hairdryer. To directly estimate a transient response for the hairdryer data, I pull down the estimate pop-up to correlation models. That opens a window where I can make a few choices, but typically the default choice is good. Pressing estimate computes a transient response and inserts it into a model board here. I look at it by checking the transient response block. Now I can look both at the step response and at the impulse response. This is a discrete time model now. It is natural to compare this directly estimated step response with the responses of the good parametric models M3 and M3DIST I had from before. And we see that they are practically indistinguishable, which is a good reassurance that the model is on the right track. To directly estimate the frequency response, I pull down the menu to Spectral Models. That opens another dialog with some choices to make. I press Estimate for the default choice, and the model SP100 is computed and inserted into the board. I can look at its border plot by pressing frequency response. And here we see the amplitude curve and the phase curve of a model for spectral analysis. Of course, I can compare these responses also with the frequency responses of the parametric models. The final estimation topic I want to bring up is that of model uncertainty. It is clear that any model we estimate will not be a perfect system description. Even in an ideal situation where a true model structure is known, the estimates will be affected by the disturbances in the estimation data. That uncertainty can be estimated from data and represented as confidence intervals of model parameters. Those in turn can be translated to confidence bounds on any model characteristics that we may be interested in. Let us study that for a hairdryer model. Take a particular model like TF3 and look at its step response. How reliable is this step response, and how much does it depend on random disturbances in the estimation data? To see that, we choose an options menu, show 99% confidence intervals. And we see here by dashed dotted lines how much variation that could be expected in the step response due to the disturbance in the estimation data. We see that the transient stage is rather certain, but at steady state gain we have about 10% uncertainty from 0.8 to 1. Similarly, we can look at the border plot of a frequency response. And if I turn on the 99% confidence intervals and I enlarge the plot to see it better, we see that relatively speaking, the amplitude is more certain at low frequencies than at high frequencies. I can zoom by drawing rectangles in the plot if I like to examine the plot in more detail. I can also turn on these grids if you like to measure the sizes of the errors. Now, due to logarithmic amplitude scale, we don't see the absolute values of the errors in the amplitude. So if I change to linear amplitude scale, I see more clearly that in real terms, in actual terms, the response is more uncertain at low frequencies. And we see here at the steady state gain, we have about 10% uncertainty between 0.8 and 1, just as we saw in the step response. We can also look at the zeros and poles of the model. And we can examine, we see here 3 poles and 2 zeros. And we can examine the uncertainty of these quantities by again checking the show 99% confidence intervals. And we see here the regions in the complex plane where the poles and zeros may vary due to the uncertainties in the estimation data. Also, simulations uncertainty can be evaluated in a similar way. So the bottom line of all this is that you can never rely 100% on a model, but it is very useful to take a look, just as we did, on the reliability of the different aspects. Just keep in mind that these measures are relevant only if the model is in an essentially correct model structure. That is, if it does not fail in the residual analysis test. When we have obtained a final model, it is a matter to put it to work. Typical tasks are to analyze system properties and to simulate and predict responses of a system. The Identification Toolbox comes with dedicated Simulink blocks that can be directly used for Simulink simulations of the estimated models. You can also directly import the estimated models into SISU tool and the MPC design task for controller design. A useful application is to use the Identification Toolbox to simplify complex systems. For example, a Simulink system can be simulated to produce data from which simplified approximations of complex subsystems can be built by system identification. The workflow for using models for control systems design basically goes as follows. Collect data from a real system. Estimate the plant along with model uncertainties. Also build a model for what disturbances affect the system. Bring the uncertain model with disturbance descriptions to your favorite robust design procedure. Then create a controller that is robust, both with respect to model uncertainties and the system noise. Well, this is the end of the seminar. I look forward to any questions you have that have been triggered by the discussion. You can also find more relevant information about these MathWorks on these MathWorks web pages and in several textbooks on the subject. Thank you.